And the next presentation is coming from the material segment. So we have Kaien Chang, Vice President of Technology overseas at leading paste supplier Solamet. He is going to talk about Solamet's low temperature paste development for next generation heterojunction perovskite tandem cells. Kaien, the floor is yours.
Yes, let me share my screen, make it a full screen. Okay, so let me probably quick go through the agenda today. So I think first of all, I want to spend 1 minute to introduce the Solamet. I think I think most of people know that we used to be n-TOPCon Solamet, and Solamet used to be our brand name. So now we are starting from the 2021, we are independent company, and now I will use our previous brand name Solamet as our current company name. So right now we have the headquarters in Shanghai, but still just like the old time that we still have the dual technical centers located in China, Shanghai, and also in Taiwan that to support our customers in China and outside of China, respectively. So I think I would just move to talk about today's topics. What will be we are going to focus for today's talk. I think that we are focusing on the low temperature metallization roadmap, and for today's presentation, I'm going to talk a little bit about our offerings for silver coated copper for HJT application, and also I think that we are also going to talk about the ultra low temperature paste for perovskite, especially for the temperatures, the curing temperature lower than 130 degrees Celsius. So here is just to give you a quick look about the overall our technical roadmap for low temperature paste from Solamet. So I think we actually have the low temperature paste from 2009, which is the PV412 and PV416, which is the thermoplastic low temperature paste for CIGS application. And I think after that, because of the booming of HJT technology, I think that we also have the low temperature offering for HJT paste. And I think that now we are focusing on the silver coated copper paste in order to improve the overall cost structure for HJT application. And as you can see that we also now also one of the important target we are going to talk about today is the ultra low temperature paste for perovskite, which we are making compatible for low temperature down to 100 to 130 degrees Celsius. And as you know that because comparing to the firing through the firing type paste, I think that because of the much lower curing temperature, we are able to make a silver coated copper paste available now. But for the next step, I think that seems that we are now able to make the curing temperature down to, just like I mentioned, 100 to 130 degrees Celsius. So I think we believe it's also possible to make the next wave of innovation to move to, for example, the copper powder paste or even the no silver paste, because that now the curing temperature is even much lower comparing to the HJT. So I think you can see that for the future HJT and perovskite on our roadmap in the next few years, I think that will be possible to move into, for example, the copper powder paste or the no silver paste, because of the now we are able to lower down the curing temperature down to like 100 or 110 degrees Celsius. So I think that will be our ultra goal for this low temperature paste. Here I would just want to spend on one page to talk a little bit about the low silver content paste for HJT. This page, I think, is the silver coated copper paste. I think in the markets now, in general, I think now the silver content probably is around 50% of the silver in the markets right now for HJT application. And this is our latest result internally. As you can see that we are able to successful to make the low silver coated copper paste. As you can see, the silver content can be lower to like a 35%, and we are still able to achieve relatively reasonable conductivity. The resistivity still can achieve 6.5, and also the contact resistance also can achieve a very similar level to the pure silver paste, 42A. So, and also we also confirm this low silver coated copper paste on the different source of wafer, including the front side and the rear side, by checking the contact performance. And also, as you can see, that we are able to achieve very similar contact performance comparing to the pure silver paste. So I think that it looks like by this new concept system with the much lower silver contact silver coated copper paste, I think that's we actually are able to achieve, I think, a reasonable resistivity, and also still the very similar contact performance to a pure silver paste. So I think this is the latest result we achieved internally. I think very soon that we will try to test this concepts in the markets. Next, I'm going to start to talk about the ultra low temperature for perovskite. So right now we actually have the two systems in the market to be tested. One is the thermoplastic system, PV43B, and the other one is the thermal setting system, 43C, which is kind of much more similar to the current HJT paste. And as you can see, there's a different feature for these two paste. For 43B, the thermoplastic one, as you can see that this one actually, because it's thermoplastic, so the feature for this one is can be operated in the room temperature, just like the current fire type of paste. So we believe this can bring huge benefits in the mass production to save the cost in terms of the wastage or in terms of the transportation. And also for this thermoplastic system, it's also enable the lowest curing temperature. You can see the curing window can down to 100 degrees Celsius because this is kind of a low temperature sintering system. And also another feature, the last feature is the low laydown. But of course, because of the low laydown, low deposition, the line thickness will be lower. So of course, the line resistance will be a little bit higher comparing to the PV43C. And for the 43C, the feature, I think just like I mentioned, is the feature is much more similar to the current HJT paste, which is the thermal setting. You need to store and transport it in a low temperature. But on the other hand, it provides a better aspect ratio comparing to 43B. So there's still have some difference or for those two different systems for ultra low temperature paste. So next page, a much more detailed introduction about the 43B, the thermoplastic one. I think you can see that if you tested the curing temperature for HJT paste and also the 43B at the 200 degrees curing temperature, I think both you can see can achieve a pretty good resistivity. But if you test it at the much lower curing temperature at 130 degrees Celsius with 10 minutes, I think that you are able to see this 43B achieve a much better resistivity. So I think, as you can see, this is the breakthrough to try to enable to make it to such low curing temperature. And also, just like I mentioned, you can see the silver content is also much lower to the traditional HJT paste. The silver content is just only 85 to 88%. And also, and for 43B, the thermal setting system, although it's much similar to the HJT paste, but as you can see, comparing to the 43B, the aspect ratio is much better. You can see the picture here. But of course, if you look at the laydown, the deposition, it will be much higher than 43B. I think could be a pros and cons at the same time. From cost point of view, of course, the laydown is higher, but on the other hand, the line resistance also could be better because of the higher thickness. So if you look at the resistivity performance, I think as you can see, under 130 degrees Celsius, I think 43C can even achieve better resistivity comparing to the 43B, but of course, much better comparing to the traditional HJT paste. So I think one of the reasons for the resistivity is better than 43B is that, as you can see, the silver content actually will be more closer to HJT paste, which is similar to, which is like, for example, 93 to 94%. And here, just give you much more detailed information about the curing temperature window for the different paste. As you can see, for 43B, just like I mentioned, you can see that basically the curing temperature can down to 100 degrees Celsius. We still can achieve a acceptable resistivity under 100 degrees Celsius. And you can see for our first version of 43C, the T5780, we are able to achieve a pretty good resistivity under 130 degrees Celsius. But you can see, when you're down to 110, then you see much higher resistivity. But by the further optimization in from inorganic and organic, right now I think that for the following 43C series, like X3005, I think right now we are able to achieve pretty good. The window, the curing temperature window, can down to like 110 degrees Celsius, as you can see in this chart. So I think that this also gives us an implication that for the different target curing temperature from different customer, I think that we might need to pick up the different paste to get the best performance in terms of the resistivity. For example, if you want to get the best resistivity under 130 degrees Celsius, of course, for example, the T5780 could be the best choice. But if the curing temperature just 110 degrees Celsius, then X3005 probably will be the better option. But if you need to go to curing temperature at 100 degrees Celsius, so far I think only 43B, the thermal process, can achieve. Next one, I'm going to talk a little bit about the current pan for low temperature metallization paste. I think, as from the current feedback from HJT customer, I think we all know that for low temperature paste, comparing to the firing type paste, I think because of the printability concern, that we are not able to achieve a very high printing speed, and also the finger opening on the screen will be wider comparing to the current fire type paste. And of course, because of this, you can just only using the wider opening screen. Of course, the laydown will be also much higher comparing to the firing silver paste for PERC or even n-TOPCon. So I think one of the current pan for low temperature paste is trying to solve the printability issue to make us to improve the throughput, and also can make it compatible with the narrow finger opening, that to reduce the overall cost from paste point of view. So as you can see that we try this kind of different screen opening pattern to try to understand the printability for the different paste. So you can see that we have the opening, different opening on one screen from 10 to 20 micron. And then we check the resistivity for each line. And then you are able to see this kind of a result. So for example, for PERC mono frontside paste, the fire type paste. Of course, for the PERC mono frontside paste, we are actually doing the firing in order to check the resistivity. But for those low temperature paste, we just do the curing like a 200 degrees Celsius. And then we check the resistivity at the different opening. And you can see, of course, the fire through type paste, they perform pretty good resistivity, even at the 10 micron opening. But for HJT paste, of course, starting from 40 micron, you are still able to, you start to see the very high resistance because of the finger interruption. But if you look at the 43C, of course, that we are now able to achieve a better performance than HJT paste. But if you look at the 43B, you are able to see you can achieve a very similar performance to the current fire paste, even at the narrowing finger opening, like a 10 or 12 micron opening. So I think this gives also an application by this kind of a 43B system. This is very high potential to solve the current pen, the current pen for low temperature paste. And further improve the throughput and also the cost issue from lower laydown. So this is just another page for the microscope pictures to let you know the permeability difference from 10 to 12 micron. So you can see for the right hand side, the right hand is the PERC fire through paste. You can see that from 20 to 10 micron. Of course, at the 10 micron, you start to see the very clear finger interruption. But at the 12 or above 12, I think the permeability still looks good. And if you look at the incumbent, the HJT paste, you are able to see the very severe finger interruption starting from, for example, even from the 17 micron opening. And for 43C, you are also able to see the permeability issue. Of course, the 3001 perform better, but still, you start able to see the finger interaction from 12 micron. But if you look at the 43B, the thermal plastic one, I think just like the previous page we show from line resistance data, I think it's aligned with the microscope observation that even under 10 micron opening still perform the very good light uniformities, that no finger interruption. So this is the last page. I think this is the last page. I'm going to also show you some of our external progress for our ultra low temperature paste in the markets. So as you can see, we have been tested at several customers in China or outside of China. I think you can see that at some of the customer in China or in Asia or Europe, some of our paste has been selected as a screen printing solution baseline. And based on the different customers' curing temperature, I think some customers they prefer 43B and some customers they prefer 43C, considering the different curing temperature or the different mass production consideration. But in general, you can see that for our 43B and 43C, they are generally can perform the tier 1 performance or even the best performance under such low curing temperature from 100 to 130 degrees Celsius. And even also from one customer, actually by small areas perovskite cell tandem cell testing, we are able to show the very close efficiency to vapor deposition solution. So I think that we are keeping to work with our customer to further fine-tune our system, no matter for thermal plastic or thermal setting system. Okay, so I think this probably is all for today's presentation.
Okay, thank you very much. And since I'm running a little bit late, so I just would like to continue with the next presentation. Can you please stay online? And there are actually a few questions in the chat window. Could you please answer them?
Yes,
Thank
sure.
you.